Hi, my name is Pratham Hitna, and I'm excited to present my project Brain Tumor Detection using Machine Learning. The goal of this project is to automatically classify brain MRI scans as either tumor or no tumor using machine learning, without applying or deep learning or black box model. This kind of solution can help medical professionals quickly detect tumors and assist in early diagnosis. For this project, I labeled dataset containing MRI brain scan images categorized into two classes, tumor and no tumor. The datasets were organized into training and testing folders. One of the first steps I took was the clean data. I found and removed 191 duplicate images using hashing. I also verified that there was no missing of corrupted files which ensured smooth training later on. Features engineering and instruction. Instead of feeding raw images direct, I extracted statistic features from the image OpenCV and using NumPy. These features include mean intensity, average brightness of the image, text variance, skewness, edge sharp, symmetric score. These features are clinically relevant. For example, tumor images are often higher variance and lower symmetry compared to the health scan. After feature extraction, I perform exploratory data analysis to understand the pattern of the dataset. Some instance tumor images that had higher texture variance, lower symmetry in tumor images, and sharper edge compared to the non-tumor ones. I validated the insight and statistically hypothesizing using t-test and correlation method to confirm whether the difference in the feature was significant. These steps gave me more confidence in the feature I used for training. So these are the pictures that I used in the MRI images as per class. Moving forward, I use data visualization. I used total 6 charts of data visualization, which include the bar graph of the brain tumor class, the proportion of tumor type, again the bar graph of image count per class folder, fourth the image file size distribution per class, fifth was the image count and the share per class, and sixth total scale view of image count per tumor class. There are a total of three hypotheses. The first hypothesis is there is significance of difference in mean intensity between tumor and non-tumor MRI images. The second hypothesis was tumor image tends to have lower symmetry score than the non-tumor images. A third hypothesis, edge sharpness is positively correlated with the presence of tumor. Moving on to the model training and evaluation. Now going to the model training and evaluation. I trained three types of different models. Logistic regression, the second was SVM, which is also known as support vector machine, and third was random forest. Before training, they scaled up the feature and applied truncated SPD to reduce dimensionality. To fix class bands, I used smooth to generate synthesis samples of the minority class. I then evaluated each model using accuracy, precision, recall, and F1 score. Random forest performed with the best around 92% accuracy and a high F1 score, so I selected it as the first model. Once I had the final model, I used its job job lib and I also saved the SPD transform to ensure consistency between the training and the real-time prediction. This made it easy to load the model back later and predict a new unseen data. Of the best part of this project is a streamlined app that I built to deploy the model in a simple interaction. The app has two models, image upload mode and the second was manual input mode. Moving to the app, this is the app that was deployed after the project. It has two options that upload an MI image and second or enter in numeric value. If we put the value of mean intensity of 130.4, texture variance of 2450.8, skewness of 1.12, edge sharpness of 410.7, and symmetric score of -7.40, it predicts the score of tumor detected with a confidence level of 52.0. If we change the value to 104.2 to 1725.5, then 0.45, 352.3, and last minus 18.9. So it shows the value of brain tumor detected, which is also has a confidence score of 52.0. This approach is lightweight, explainable, and fast, unlike the deep learning machine that needs a lot of power. It's ideal for real-world hospitals which resources are limited, and because of its clinical features, the output is easier and explained and trusted. Personally, I learned a lot about data processing and image analysis, statistical learning, email, ML evaluation, and deployment. This was just a technical project. It was about building something that I can make a real impact. To summarize, I built a clean ML pipeline for tumor detection using statistic feature for MR image, trained the evaluation in multiple models, chose the best one to deploy using Streamlit, and made the app simple, suitable for real users. This project shows how classical ML and domain knowledge can work together to solve a real-world problem. Thank you so much for going through the video. I hope you found it helpful, and if you have any question and suggestion, I'm happy to answer that all. Thank you.